All right, on to our last video for the week. This is again section 13.5, and we're to part 2, planes. We're going to look at equations of planes in 3 space. So a plane is what you think it is. It is basically an infinitely large piece of paper just sort of going in space. So there down below is a picture from our textbook, which I think is a really nice simple text picture to kind of talk about what we're going to do. There's a plane. So we need to think about, what is it that we need to be able to define a plane in space? The geometry definition is that we need 3 points. If you've got 3 points sitting in space, that defines a plane. But some other things that we could use to define a plane in space is that we could use 1 point, and a vector perpendicular to our plane. So that's essentially the picture that we have right down here. So the idea is if we only have 1 point on our plane, so like this one particular point that we're given, and we want to go off into different directions and look for other points, if we go off into the direction here and get to this other point, if we're going off into another direction to get to another point, we don't know exactly where to go. It's kind of, we can think about if we're just looking at that one vector, if we only had 2 points, that plane would be wobbly. We don't know which way we need to go. It would kind of sit along that line that's a vector, but it could wobble back and forth. So what that normal vector does is it grounds that plane into space and says this plane needs to be perpendicular to this vector n. So our sort of fancier definition, a way to say this is that given a fixed point, p sub 0, so fixed point meaning that that's a point we're going to know, that's going to have actual values, and a non-zero normal vector n, so n is that vector that's perpendicular to our plane, and again, that's a vector that we're going to know, it's a vector with numbers, and then the set of all points p, so those points p, those are going to be our variables, those are any other point around that sits on our plane. And again, we're in R3, for which that vector starting at p sub 0 going to p is orthogonal to that normal vector is called a plane. So it's basically all the points surrounding p sub 0 that we can go off and make a vector, and we're staying perpendicular to that normal vector. So, all right, what is this vector, p sub 0, p? What is that going to look like? Well, the point p sub 0 is x sub 0, y sub 0, z sub 0. That's a specific point. Those are going to have numbers there. So when we've got those subscripts, that means that has numbers, and p not having subscripts, meaning that's going to be a variable. That's some random point on our plane. And so this vector is going to be x minus x sub 0, y minus y sub 0, those component parts being subtracted. We've done this a lot. Okay, now we also know it is that this vector that we make between those 2 points, it's orthogonal to that normal vector n. So remember, n is that vector a, b, c. So our normal vector, if we do the dot product with our p sub 0 p vector, we should get 0 because these two are orthogonal. And so that vector ABC, if we do the dot product with our vector up above, this is equal to 0. This is actually going to give us how we're going to write our equation, because if we actually do this dot product, remember the dot product is the x components multiplied together plus the y components multiplied together plus the z components multiplied together, and that's equal to 0. That's an equation, because that regular x, y, and z, those are our variables. And then a, b, and c, those are numbers. A sub 0, b sub 0, c sub 0, those are numbers. So this is going to give us an equation. So that's so cool, because now we can have the general equation of a plane in R3. So we've got our plane that goes through our given point, and then we're going to have that normal vector. And then the equation of our plane is that x component of our normal vector times x minus x sub 0, the b component of our normal vector times b our y minus y sub 0, and that c component of our normal vector times z minus z sub 0. And this is going to be equal to 0. Now we can do all the multiplication here, the three distributive properties, and get things all moved around so that we've just got ax plus by plus cz is equal to d. And d is equal to this. You don't need to remember that. I'll show you how we get it. It's just making our equation look nice. This is sort of like going from point slope right here to slope intercept form. They're the same equation. You could leave it technically in that first format, and it's not wrong. It's the equation of our line. The second format just looks a little nicer. Okay, so let's take a look at a quick example here. So if we're given a point and a normal vector, so this is our x sub 0, y sub 0, z sub 0, and this is that a, b, and c. So the equation of our plane, so remember it was this. It really just is a matter of plugging things in where it goes. And yeah, we're remembering that this came from us finding that vector, from this point here to any other point on our line, and the dot product with our normal vector being 0 because it's perpendicular to um, that vector that we've got in our plane. So it really is just a matter of plugging everything in where it goes. And technically, just like when you're using point slope formula of a line, that's the equation of our plane right there. That's it. Now, I'm kind of one of those people that I just like my equation of my line to look nice, or my equation of my plane to look nice. So I go ahead and do the distributive property, and you end up with, a bunch of constant terms that you can add together. Oh, stop it. There we go. And so we get 4x plus 2y plus 2z is equal, or minus 24, excuse me, adding those up is equal to 0. And just adding that 24 to both sides, it just looks nicer. So this is generally how we give our answer. Okay, let's take a look at another example. So I did mention that one of the ways that we can define a plane is with 3 points. So let's look at what happens if we have 3 points. So what we need to do, what we're missing here, kind of like with our lines, is when we're just given points, is we're missing that slope. We're missing, the direction that we're going. So what we need here, though, instead of the direction, is we need that normal vector. We need that vector that's perpendicular to our plane. Well, we can find perpendicular vectors. So if we take and create some vectors out of these points, so if we go from P to Q and make a vector, so we can do that. That's taking, again, our component parts and subtracting them. So we're going to get, 2, -3, and 3 for that first vector, and then we could go to P to R. You could go from Q to R, or R to Q, or R to P. You can do any combination of vectors that you want. It's up to you. You just need to make 2 vectors that are in your plane. Because once we have 2 vectors that are in our plane, we can use the cross product and find the cross product of these 2 vectors. And that cross product is perpendicular to both of those vectors. And that's going to give us our normal vector, which is what we need. We need that normal vector. So we'll go and find the cross product. So we set up our big determinant here. Okay. And so as a reminder, we get our little 2 by 2 determinants. So not using the I column to make our 2 by 2 vector, our determinant for I, the coefficient of I, not using the J column to get our 2 by 2 determinant for J. I always want to write K first. So if you do that too, every time, and it's in darn alphabetical order, shouldn't have that problem. All right, and then our determinant for our coefficient of K is using the 2 columns that are not the K column. All right, so again, remembering each of these, we multiply and subtract, we multiply and subtract, and we multiply and subtract, and we get, for our normal vector, let's see, what are we going to get here? we are going to get 9i minus plus 7j, oh, two negatives there, and plus k. All right, check my work here. Oh boy, let's see, how'd I do? What have I got there? Right, I think we're okay. Okay. Sorry, I'm just checking something that I think I had wrong on my notes. That's all right. Okay, so phew, all right, everything's good. All right, now we need a point that's on our plane. For your point that's on your plane, you can use any of the points that you want. So you can use P, Q, R. It does not matter when you're figuring out what your like initial point is. So I generally just use the one that they call P, just because. So I've got my normal vector, and then the x component times x minus the x value of my point, plus 7 times y minus the y component there, plus 1 times z minus the z component, and then this is equal to 0, so 9x minus 9 plus 7y minus 21 plus z minus 1 is equal to 0. And all together, this is 9x plus 7y plus z is equal to 31. All right. Okay, next question. Finding the line of intersection of two planes. So we've got two planes. They're going to intersect, and where they're going to intersect, it's going to be infinitely long. It's going to be a line. So if we're thinking about what we need to find the equation of a line, we need a point that's on that line, and we need the direction that it goes. So one of the things that we can get from these two lines here, or two planes here, so we've got plane 1 and plane 2, is we can get those normal vectors from each of those planes. And the line where these two intersect, it lies on both planes. So our line is perpendicular to both of these normal vectors. So if we want a direction that is perpendicular to two vectors, we can get that, I better put subscripts on those, huh? By doing the cross product of those two normal vectors. That's going to give us a direction that is perpendicular to both of those normal vectors, which is what we want. All right, so let's do our determinants here. 2, 3, 1, 1, and k. There we go. So we should end up with a positive 3 here and a minus 7 here. I'm doing some addition and multiplication in my head here. Yep, and then we should end up with a minus 1k there. So this is the direction of our line. Now what we need, because we need one more thing, we need a point that's going to be on our line. We can pick any point that we want. So something that we can do, and this again feels like one of these like cheap math things that we do, is that we can say, okay, let's let z equaling 0, because there's going to be a place on this line where z is equal to 0. There's going to be a place where these two planes intersect when z is 0, because there's infinite number of points on this line that we have where they intersect. So let's specifically look at what happens when z is 0. Now we can do this again, totally feels like a trick, but we could do this little trick here with x being 0 or y being 0. What we're basically figuring out here is where these two planes intersect in the xy plane when z is 0. And what this does by letting one of our variables be equal to 0 is we've got a system of equations in two variables, and so we can do, multiplying this guy by -1 And we can do the elimination rule by adding those two together, getting x is equal to 9. So if z is equal to 0, that means x is going to be equal to 9. Then we can plug this back into either one of our planes. It really doesn't matter. And figure out what y is going to be. And in this case, we get y is equal to negative 22. This is exactly what we get if we plug it into the other plane, which is the whole point. It doesn't matter. It's sometimes nice to plug it into both to make sure, oh yeah, we do get negative 22 again. So what we found is that the point 9, negative 22, 0 is on both planes. That is a point that's on both planes. So now we know the direction that our line needs to go in. We know the point that's on both of our planes, so that's on our line of intersection. And now we just need to write our equation of our line. So we can write the vector equation if we want. So it's that point made into a vector plus, again, that variable scalar times our direction. Or we can write the parametric equations if we want. So we get x is equal to 9 plus 3t, y is equal to negative 22 minus 7t, and z is equal to negative t. There we go.